Hi everyone, this is Matt Touchot with Intro Stats, and today we're looking at one of the more difficult topics, the Quantitative Association Hypothesis Test, generally known as correlation and regression. So let's get started. So just a few things to remember. This is sort of the follow-up to the actual correlation and regression sample video where we talked about the correlation coefficient R and scatter plots and things like that. Now we're sort of taking the next step and actually doing the actual hypothesis test. So remember we need random sample data, usually ordered pairs, quantitative data. And we're trying to now see if these two quantitative variables are somehow related in the population. Just a few letters to keep in mind. Of course, R is the sample correlation coefficient. Sample slope of the regression lines. Different computer programs use different letters. I tend to use B1 for the slope and B0 for the y-intercept. The population correlation coefficient is the Greek letter rho. It kind of looks like a squiggly P. So sometimes you'll see that in the null and alternative hypothesis. Also, if you're doing a null and alternative hypothesis based on the slope, the population slope is generally denoted as the Greek letter beta or beta 1. So those are just letters to keep in mind. Okay, so we saw in our last section, our last video, that the slope of the regression line is actually related to the correlation coefficient. We calculated the formula that the slope of the regression line is actually the correlation coefficient R times the standard deviation of the y values divided by the standard deviation of the x values. So the main thing to take away from this is that when there's no correlation, we saw last time that our R value goes to 0. But what happens to the slope? If you look at that formula, R times standard deviation of y divided by standard deviation of x, if the R was 0, that formula would also go to 0. So the key thing about this idea is, and this is sort of why people sometimes use correlation coefficients R, or they use the slope to do the hypothesis test, is because as both of them go to 0, you have no correlation or no quantitative relationship between the variables. So just think of it as, again, as the R goes to 0, or as the Greek letter rho, the population correlation coefficient goes to 0, the population slope beta 1 will also go to 0. So you'll see that in the null and alternative hypothesis. All right, so there's different kinds. Again, a quantitative association test can be two-tailed, right-tailed, or left-tailed. They often use the t-test statistic, though you don't necessarily have to. You could base your significance decision on the correlation coefficient itself or on the slope itself. So let's start with the first one, the two-tailed correlation test. Again, this is usually determined to see if there is some relationship or not. So is there a relationship between the two quantitative variables? So there's two ways of writing it. You could write rho equals 0. Remember how we say that's the population correlation coefficient. And that would indicate not related. Okay, if the rho was not 0, if the population correlation coefficient was closer to 1 or negative 1, then the two quantitative variables would be related. And again, that goes with slope as well. So if the population slope beta 1 is 0, then the two quantitative variables in the population are not related. And if the slope is significantly positive or negative, in other words, the beta 1 is not equal to 0, then the quantitative variables are related. Now we learned last time that you can also have, you can test for direct or inverse relationships between your two quantitative variables. We said that if the correlation coefficient was significantly positive, close to 1, that indicates a direct relationship. As the x variable goes up, or increases, the response variable y also increases. So sometimes we call that a direct relationship in math. So again, this would indicate a significant positive correlation. And also, it could be a significantly positive slope if you were able to base it on a critical value. This is a right-tailed test. So we're looking for either the rho, a null hypothesis would be, again, the rho is equal to 0, no correlation, not related. And then the alternative hypothesis would be rho is greater than 0. Again, this would indicate a direct relationship or a positive correlation. Again, we can do the same null and alternative hypothesis, but write it in terms of the slope if we're using slope calculations. So this also implies beta 1 equals 0. Again, not related, no correlation. If beta 1 is greater than 0, the population slope is greater than 0, then we do have a positive correlation or a direct relationship between the variables in the population. So this is how you would see the right tail test written. We can also have a negative or inverse relationship. Again, this means as the x variable goes up, the y variable goes down. So again, we would see a significantly negative correlation coefficient, and the correlation coefficient is close to -1, and a significantly negative slope. Right? So, and this would be a left-tailed test, because we're looking for either the population correlation coefficient rho is equal to 0, not related, or the population coefficient rho is less than 0. Again, that would mean it's closer to -1. If we apply that sort of same thing to the slope, sometimes you'll see the null and alternative hypothesis written this way: slope beta 1 equals 0. That means not related, and population slope beta 1 is less than 0, meaning that the population slope is significantly negative. And again, this would indicate an inverse relationship or a negative correlation between the two quantitative variables. So we can check significance using a variety of different ways. The traditional test for this quantitative association test usually uses a t-test or a t-test statistic usually based on the slope, though you can base it on other things. The t-test statistic calculation based on slope is something like this. It looks like the sample slope minus 0 divided by the standard error for the slope. Again, these are calculations that are very difficult, and again, usually you have a computer calculating these t-test statistics. Again, remember, 0 is a key number, because remember, that's where there's no relationship. Remember, the idea of any test statistic is to see how far, or see if the sample data significantly disagrees with the null hypothesis. Well, 0 is the null hypothesis, right? 0 slope or 0 correlation coefficient. So that's why that 0 is there. So the sentence for the t-test statistic is the number of standard errors that the slope of the regression line is above or below 0. Again, if the t-test statistic was positive, it would be above 0. If the t-test statistic was negative, it would be below 0. And then if we want to measure the t-test statistic or use that t-test statistic to determine significance, we could use a t-distribution, degrees of freedom n minus 2. That's the number of ordered pairs of data minus 2. And see if the t-test statistic falls in the right or left tail based on a critical value. We'll show you examples later here. But you could also use randomized simulation. A lot of times you can calculate or computer programs often give you a critical R value. So if you wanted to use, instead of calculating the t-test statistic or using the t-test statistic, you could see if the sample correlation coefficient falls in the left or right tail based on the critical R values the computer provides you. So we'll see again some of that later in our examples. Okay, so looks like we have a little bit of a typo there, but basically the residuals. So there's two main graphs when you're looking at doing a quantitative association hypothesis test, and they both resolve around, well, there's actually three main graphs. The scatter plot, of course, is important, which shows the actual points and the regression line, but also these residuals. So we have a residual plot and the histogram of the residuals. If you remember, the residual is sometimes denoted as y minus y hat. That y hat got cut off there, but it should have a y with a little hat on top of it. So y minus y hat, which basically gives you the vertical distance that each point in the regression line is from the vertical distance, how far each point in the scatter plot is above or below the regression line. That's a better way to say it. So remember that the residuals always have y units. It's whatever your response variable is. That's going to be the units of the residuals. When a residual is negative, that means the point is below the regression line, and when a point is positive, it is a point above the regression line. So these residuals are important to analyze when you're dealing with a quantitative association test. And there's two main graphs that we like to look at. One of them is called the residual plot, which is basically just a graph of these residuals with a zero line kind of representing the regression line. And then it kind of shows you, it kind of is like a magnifying glass, kind of shows you how far up and down from the line points are. And then you have the histogram of the residuals. Remember, in any time you're using a t-test of any kind, you need to know if the data is normal. And so we often look at, instead of looking at the histogram of the individual quantitative data sets, we like to look at the histogram of those actual residuals. So this shows, again, the shape of the data, and we also like to know if it's centered close to zero. So there are definitely different kinds of residual plots. This is a deep well. I mean, this is a really tricky subject, and you can, especially for an intro class, we don't like to get too far down that rabbit hole. But the main residual plot that is very useful is the residual plot versus the x values. Again, it looks like kind of I like to think of it as a magnifying glass on the scatter plot. It just makes the dots, a lot of times in a scatter plot, it looks like thousands of dots and it's just a big mess. But the residual plot kind of makes it bigger and you can see the actual distances better. So one of the key things with the residual plot is that you want it to be sort of evenly spread out. In other words, the points above the zero line and below the zero line have to be sort of evenly spread out. You don't want the points close in one area and far away in another. Sometimes that's called a kind of a sideways V pattern or a fan shape. If that happens, that can be problematic. If you guys remember in our last section, we talked about the standard deviation of the residual errors. Well, that standard deviation of the residual errors wouldn't be as accurate if you had a fan shape or a sideways V pattern. So here's an example of a residual plot. We're seeing this is the residuals versus x values. This is men's ages was the x. I believe the y's were cholesterol. And we had a computer program create a residual plot. And what you're seeing here is that on the left side of the graph, the dots are very far from the zero line. You see that horizontal zero line. You can see how the dots are very far from the zero line on the left side of the graph. But on the right side of the graph, the dots get much closer to the zero line. We don't have very many dots far away from the zero line. This is sometimes called a fan shape. What you're seeing is sort of the fan that you fan yourself with. It's kind of very wide on one side and then it goes very narrow in another side. This is problematic and it would fail the even spread assumption. So again, we also need to check, of course, most t-test statistics usually have some sort of 30 or normal requirement. We can check if we have at least 30 ordered pairs in our data, but we also need to check shape. And again, one of the things we like to do is look at the histogram of the residuals. So the computer calculates all those residuals and just makes a histogram of it. And there's two different things we check. So obviously it should be nearly normal, pretty close to bell-shaped. And we do want the center of the histogram, the highest bar, should be pretty close to 0. Remember, that 0 number is important. That's where our null hypothesis is based. So here's a good histogram of the residuals. This one was from men's weights, and what we're seeing here is the y variable was men's weight, and what we're seeing here is that it is relatively, not perfectly bell-shaped, but it is relatively normal. It's pretty close to normal. It's not doesn't look very skewed right or skewed left, so it would pass that condition. Also, it has a little 0 line. This graph again was calculated with a program called StatCato, but a lot of other programs look very similar. The 0 line, there's a vertical 0 line right in the middle, and you can see that's very close to the highest bar. In fact, it's right on the highest bar. Usually what we want is that 0 line to be pretty close to the highest bar. What we mean by that is that the data should be centered close to 0. So when you're looking at these kind of histogram of residuals, you're checking, is it normal and is it centered at 0? All right, so the quantitative association test, correlation and regression, is probably one of the toughest hypothesis tests. I mean, it really is. I mean, you can study this stuff for a long time, and there's a lot of different conditions involved. I put the most common ones here, and just to kind of give you an idea of what statisticians and data scientists like to check when they're actually doing a correlation and regression study. One of the things is, of course, that we should have good data. Our data should be collected randomly, so it should be random ordered pair data, or at least be representative of the population. The data values within the sample should be independent of each other. This is always a difficult one. Remember, this is ordered pair data, so the data values between the samples will be connected because they'll be coming from the same people or same objects. But within the data, within each data set, the people or the objects in the ordered pair data should not be related to each other. The individual observations that you're taking, so their ages or maybe their cholesterol, should not be related to each other. If I was dealing with cholesterol, I wouldn't want people from the same family because they all may have similar cholesterol levels just based on genetics. Of course, our sample size should be at least 30, so we should have 30 or more ordered pairs. When we look at the scatter plot, we should see a linear pattern. We kind of talked about this last time with the correlation coefficient, and that would indicate that the correlation coefficient should not be close to 0. Usually you should always look at the R and the scatter plot together, right? Because they both tell a story. In the scatter plot, you're going to see that the dots should be pretty close to the line following the regression line, and the R value should not be very close to 0. That's one of the telltale. If your R value looks pretty close to 0, it probably is going to fail that condition number 4. Condition number 5, there should be no influential outliers in the scatter plot. So we talked about last time that some dots look like they're just way off from the regression line. And remember, this is based vertically. What we're really looking for is the vertical distance from the regression line is very far. If that happens, that's called an influential outlier. And how do we know it's influential? Well, the R value will start taking a hit. If you really have no influential outliers, your R value should be pretty close to 1 or -1. If your R value starts dropping, getting closer and closer to 0, you probably have some influential outliers. You probably have some dots, and again, you'll have to look at the scatter plot. You'll have some dots that are vertically very far from the regression line. One thing to keep in mind, the residual plot is a magnifying glass. Everything looks like an outlier in a residual plot. So don't look for outliers in the residual plot. Look for outliers in the actual scatter plot. Obviously, we said already that the histogram of the residual should be nearly normal, and it should be centered close to 0. And we should not see a fan shape or a sideways V pattern in the residual plot versus X values. Again, it should be evenly spread out. Okay, I think that'll do it for now, and we'll pick up again with some examples. Talk to you next time.